G'day, g'day. This one I just wanted to take you through a complete problem. We asked to sketch something. So if we had to sketch y equals 2x cubed plus 6x squared minus 12, how would you go about that? Now, I know you could find this, you could use factorization, you could find general equations for these, but what I just want to show you is the procedure for using derivatives in calculus for making this easy to sketch. So, first thing to do when you want to know what turning points are and points of inflection, that sort of thing, we want to know our derivatives. So, our derivative, firstly, dy by dx is equal to 3 comes around the front, that's 6x squared plus 12x. Fantastic, there's dy by dx. And our second derivative is dy by dx squared is 12x plus 12. There we go, so there's our second derivative. That's a good start. Now, to find our stationary points, so we want stationary points. And how do we find our stationary points? Well, that's when dy by dx is equal to 0. And so therefore we get when this is equal to 0 here. So when I'll just factorize it in one go. So therefore, when 6x plus 2 is equal to 0, so therefore we'll get when x is equal to 0 and when x is equal to negative 2, they will be our stationary points. Okay, and so just to get our actual coordinates, 0 and 0. Oh, sorry, I'm looking at the wrong one. I was looking at derivative. Back to the function, when x is equal to 0, y is equal to negative 12. And when x is equal to negative 2, y is equal to negative 8 times 2, negative 16 plus 24 is negative 16 plus 2 is positive 8, negative 12 is negative 4. So they're our turning points there. Okay, fantastic. Now, are these maximum or minimum turning points? And so it's just good to figure this out. So when x is equal to 0, the second derivative, let's have a look at what the second derivative is when x is equal to 0. When x is equal to 0, the second derivative is equal to 12x plus 12. Okay, so we get 12 times 0 plus 12, which equals 12. Now, because this is greater than 0, what this means is that your gradient is increasing. So it's getting bigger and bigger and bigger. And basically what that means, because if it's negative and it gets bigger, 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 hits 0 and then gets bigger, 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 what you'll get is a local minimum at that point. So x equals 0, it's going to be a local minimum. Let's have a look when x is equal to negative 2. What you're going to get your second derivative at that point is equal to, second derivative when x is equal to negative 2, you'll get negative 24 plus 12. Now that is less than 0, I don't care what it's equal to, but it's less than 0. And what that means is that it's getting smaller and smaller, that gradient. So it's big, and it's becoming smaller and smaller, it gets to 0, keeps getting smaller and smaller and smaller like that. What that's going to be is a local maximum. Okay, so when the second derivative is less than 0, you get a local maximum. When it's greater than 0, you get a local minimum. Okay, so that's a very useful part. You don't need to do your sign diagram sort of thing, negative 2, 0, and figure out that sort of thing. You don't need to do that sort of rubbish. You can just use the second derivative to figure out if it's local min, local max. Okay, fantastic. Let's go and have a look at points of inflection. Points of inflection occur when the second derivative is equal to 0. Okay, so the second derivative equals 0 will be when 12x plus 12 equals 0. Therefore, you get a point when x is equal to negative 1. And that point will be negative 1, and that'll be negative 1 cubed is negative 1. Negative 2 plus 6 is 4. 4 minus 12 is negative 8. So that's where you'll get a point of inflection. And that gives us enough information now to try and sketch this graph. So I'm just going to quickly sketch it here. And let's just have a go. So, just a rough sketch, sorry about the roughness of it. But so what we've got a local minimum, we're at 0 and negative 12. So 0, negative 12. We're going to have this local minimum. We're going to have a local maximum at negative 2, negative 4, so somewhere around there. It's not accurate. Negative 2, negative 4. And also we're going to have a point of inflection at negative 1, negative 8, so some point in there. Okay, fantastic. Also, it looks like, so if this is a maximum, so it's going to look something like that. This is a minimum, so it's going to look something like that. It looks like it's going to go like that. At this point, it would be also worth figuring out what your x-intercept is here when y is equal to 0. So I won't go and do that. You could use your calculator or whatever. I'm just going to save a bit of time. But you'd also figure out what your x-intercept there is there. So the graph looks like this. So it comes up, hits your maximum, goes through the point of inflection, hits your minimum, and comes up and goes through there. It looks something like that. And so you'd have to label all these points, obviously. Label, 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 label. Label your point of inflection, and your minimum, that sort of thing, and your intercept. So all the same things you'd normally do for any graph. But you can see how the derivative, when that's equal to 0, gives you your stationary points. The second derivative tells you whether they're maximum or minimums. And also your second derivative, when that's equal to 0, you get these points of inflection sitting right there. And so that's how we use calculus to help us with curve sketching. It's very, very useful.